In this section, we want to study the characteristics of waves, and we will start with the amplitude of a wave. What is amplitude of a wave? How is it defined? Let us look at mass which is oscillating on a spring. Over here, I have mass suspended on a spring. In this position, this system is in equilibrium. So let's identify this as the equilibrium position. And then I displace the particle, which is this mass, through a displacement of 10 centimeters. So it will move from the 20 centimeter mark to the 30 centimeter mark there. And then I release the system. You realize that the mass starts to oscillate about this particular position. Let me reduce the rate at which it oscillates so that we can be able to study it properly. So you can see this mass, this point here, is moving. Just follow my cursor, the way my cursor is moving. It's moving to and fro about this particular position. Sometimes it is on the upper side, sometimes on the lower side, and so forth. We say that the particle is moving to and fro about the equilibrium position. The maximum displacement of that particle from the equilibrium position on either direction is what we refer to as the amplitude of this oscillation. For example, in this particular situation, the amplitude is 10 centimeters because the particle has been displaced 10 centimeters upwards, and when released, it starts oscillating 10 centimeters upwards, 10 centimeters downwards, like that. It starts oscillating about this particular position. This is the equilibrium position. Now let us look at a simple pendulum. Over here, I have a simple pendulum. A simple pendulum consists of a bob, this bob here, and a piece of thread. And then the pendulum is displaced through an angle, and then it starts to oscillate. Let us reduce the speed at which the bob is oscillating in order to be able to find out the maximum displacement of this bob from equilibrium position. First of all, this is the equilibrium position. That is the equilibrium position. Now, the maximum displacement of this particle in this direction is what is referred to as the amplitude of this oscillation. So let me reduce the speed at which it is moving so that we'll be able to see displaced all that much. Up to that point, we can say that is the amplitude of this oscillation. From this point all the way up to a point like that. That is the maximum displacement of the particle from equilibrium position. And we refer to that physical quantity as the amplitude of the wave. Remember, the maximum displacement of this particle from equilibrium position is what we refer to as the amplitude of that particular wave. We can use wave on a string to show these two. Over here, I have a wave in a rope. And if I set it into oscillation, you'll be able to see that is the kind of situation we have. Let me pause the oscillations so that we can be able to measure the amplitude of this particular wave. See this particle here? The maximum displacement of this particle in either this direction or this direction is what we refer to as the amplitude of this particular wave. And that amplitude will be equal to this amplitude. It will be equal to this amplitude. So even in this particular position, we are able to come and we measure from that particular point, from this point, all the way to equilibrium position. This is the maximum displacement of this particle, and we can see that it is approximately 10 centimeters. So remember, the maximum displacement of that particle from equilibrium position is what we refer to as the amplitude of the wave. So the particle keeps on moving to and fro about the equilibrium position. Let's consider this green particle here. And we can see what it does is that it moves to and fro about this particular position here. Sometimes it's above the point, sometimes it's below the point. We say it is moving to and fro about that particular point, which is referred to as the equilibrium position. The maximum displacement of that particle from equilibrium position is what we refer to as the amplitude of the wave. Back to the pendulum, the maximum displacement of the bob from equilibrium position is again the amplitude of that wave. And also for this particular mass, the maximum displacement of this mass from equilibrium position will be the amplitude of that particular wave. So I want you to write down this definition because it is an important definition. Amplitude of a wave is the maximum displacement of a particle from its equilibrium position. Like we have just seen, this particular displacement from this point all the way to that point is what we refer to as the amplitude of the wave. It could be measured here. It could also be measured from this particular position, or this particular position, or this particular position. Wherever we have crests of a wave, this is a crest, this is another crest, another crest, another crest. That distance from equilibrium position, this line represents the equilibrium position. That distance from equilibrium position all the way to the crest is what we refer to as the amplitude of the wave. This position here is referred to as a trough. This is another trough and another trough. Again, the maximum displacement from equilibrium position all the way to the trough is again the amplitude of the wave. So I hope you've gotten what we mean by amplitude of a wave. It is the maximum displacement, and it is important that we note this, the maximum displacement. What I have highlighted here, maximum displacement. Because particles do not always have maximum displacement. For instance, at this particular point, when distance is 0, the displacement is 0. But when the distance is, for example, 1, the displacement is 3. You can see that. When the distance is 2, the displacement is 5. And when the distance is 3, then the displacement is 6. Now when the distance is 4, the displacement is 5. And when the distance is, 6, the displacement is around, it's 2. And when the distance is this particular distance here, which happens to be 6 units, the displacement is 0. So you can see the displacement of this particle changes from 0, increases all the way to 6, and then reduces from 6 back to 0. So the maximum displacement of that particle is 6. So over here we are going to say the maximum displacement of this particle is 6 units. It may be meters, centimeters, or any other unit which is used to measure distance or displacement. So let us say that amplitude is measured in meters. This is the SI unit of amplitude because it is a displacement. It is measured in meters. So very important for us to be able to understand the definition of amplitude. Let's go to the next characteristic, which is wavelength. Wavelength. So we want to define wavelength. Again, let's go back to our simulations. I want to use wave on a string to illustrate what we mean by wavelength. Now let me pause these oscillations. A complete oscillation would be from this point all the way to this other point here. That is a complete oscillation. The next complete oscillation will be from this point again all the way to this other point here, or from this point all the way to this point. Perhaps a simple pendulum would be better to illustrate what we mean by a complete oscillation. So let's go to the simple pendulum, and here we are. Now, a complete oscillation consists of this movement, this first quarter, another quarter, the third quarter, and the fourth quarter. That is a complete oscillation. I repeat. Look at the trace which is drawn by the bob. That quarter, followed by that other quarter, and then the third quarter, and finally the fourth quarter. The wave has made one complete oscillation. So a complete oscillation has 4 quarters. Now we want to consider the distance which is traveled by the wave when the wave makes one complete oscillation. For instance, if it travels 2 centimeters, another 2 centimeters, that is a total of 4, another 2, that is 6, and finally another 2, that is 8 centimeters, the wavelength of the wave will be 8 centimeters. Let's move back now to the wave on a string. That kind of oscillation is very familiar to us. Again, we are going to pause. So we have said that a complete oscillation is from this point all the way to this point. So that distance, if I can measure it like this, from this point all the way to this point, it's about 49 centimeters. That will be the wavelength of the wave. The wavelength of the wave. So let's go back here, and we will be able to see that the wavelength of the wave is from this point to this point, because this is a complete oscillation. The distance which the wave covers in one oscillation is what we refer to as wavelength of the wave. In physics, the symbol given for wavelength of the wave is lambda. Lambda. That lambda is written like this. It's just like a Y which is turned upside down. Lambda. So from this point to this point again is one wavelength. So we would represent it with this symbol, lambda. Or from this point to this point, again it is one wavelength, and we will represent it with lambda, like that. So we define wavelength of a wave as the distance traveled by the wave when the wave makes one complete oscillation. The distance traveled by the wave when the wave makes one complete oscillation. So these are very important definition, and I want you to write it down immediately in your book. I would like to emphasize that it is a distance. And then that distance covered by the wave, or the distance traveled by the wave, it is that distance which is traveled by the wave when the wave makes one complete oscillation. Wavelength is measured in meters because it is a distance. Amplitude is measured in meters. Now we are seeing the second physical quantity, wavelength, which is also measured in meters. Now let's go to the third characteristic of a wave, which is periodic time. Now over here, unlike the previous two graphs, which were, if we can go back here, you'll see that this one is a displacement distance graph. In this case, I have a displacement time graph. Displacement time graph. Now, this is one oscillation. And this is the time taken to make one oscillation. This is another oscillation. Again, this is the time taken to make one oscillation. Or we can say from this point to this point is one oscillation. Again, we can measure the time taken to make one oscillation. The time taken to make one oscillation is what we refer to as the periodic time of the wave. Time taken to make one oscillation or a vibration is what we refer to as periodic time. The symbol given for periodic time is capital T. Capital T. So this is capital T. Periodic time. From crest to crest, periodic time. Or from trough to trough, another periodic time. Or from this point here all the way to this point here, again, that is periodic time. We can also identify other points. For instance, this point all the way to this point, this is periodic time. Periodic time is measured in seconds. It is measured in seconds because it is time. Now let's look at the last characteristic, which we are going to call frequency. So we want to talk about frequency. Again, we have the displacement time graph. Now here I have several waves. We have already seen that this time here, time taken to complete one oscillation, is what we refer to as periodic time. Now, let us look at a time of 1 second from this point all the way to this point. 1 second. How many oscillations do we have there? 1, 2. 2 oscillations. So the frequency of this wave is 2 Hz. 2 Hz. We are going to see that the SI unit of frequency is Hz. But first of all, let us understand what is the meaning of frequency. Frequency is the number of oscillations or vibrations made in unit time. For instance, here I have 2 oscillations per second. Therefore, the frequency will be 2 oscillations per second, or 2 Hz. Frequency is measured in Hz or per second. Per second. So you'll draw or you'll write down s raised to -1. Frequency is measured in hertz or per second. It's very important for you to remember that the SI unit of frequency is hertz or per second. Very important. That's why I'm highlighting this part so that you can remember. So let us stop this video at this point where we have been able to define various characteristics of a wave, starting with the amplitude, going to wavelength, periodic time, and frequency.